Hello everyone. So in this video we'll be checking 5 organic chemistry conversions. So let us check the first question. So as you can see that we have been given a phenitol compound. This is an ether actually, ethyl phenyl ether, and we have to convert it into the the aniline derivative. So it will become the para ethoxy aniline. So we will check this question out, and to perform this question we will be doing Beckmann rearrangement. So it is a very very known name reaction. So we'll be doing this Beckmann rearrangement for affording this conversion. So in today's video we'll be checking such good conversions and interesting reactions that we can approach to make these conversions in the fewest steps possible. So let us see, for this one we'll be using the Beckmann rearrangement, and as you can see that we have got this ether compound, which is the ethyl phenyl ether. Firstly what we'll be doing is that we'll be using Friedel-Crafts acylation reaction, which will actually incorporate the acetyl group or the acyl group in the para position of phenitol. And after that, on the application of hydroxylamine hydrochloride, that would actually convert the the ketone part, the COCH3, into the C double bond NOH, which is the corresponding hydroxylamine compound. And this is the E isomer that I have drawn. So this would be the most stable. And after that, when we incorporate acidic media in this particular compound, this would actually undergo the Beckmann rearrangement. So firstly, what would happen is the hydroxy group that is in connection with the nitrogen would get protonated and become OH2 plus, and after that the whole the ethoxy benzene group or the phenitol group would actually rearrange, eliminating the water, and nitrogen would give its lone pair into the C double bond C. So what we will get is the nitrogen positively charged in triple bond C, and which will undergo subsequent attack by H2O, and hence it would actually compensate the positive charge of nitrogen, and we will get the corresponding imine. And after that it would actually undergo the tautomerism, and proton exchange would happen, and which would actually give us the corresponding NHCOCH3, which is the acetanilide group. And this, when undergoing hydrolysis by the application of a little bit of acidic water, it would actually give us the corresponding aniline. So it will become the para ethoxy aniline. The last step could actually simply be a acidic workup type of reaction. Yeah. Okay. So going into the second question, let us see. So we are given this compound, which is actually CO2Et, CH2, CH2, CO2Et. So two ester groups which have been given a spacer of 2 CH2. So we will be using the Claisen rearrangement to convert this into the cyclohexane compound that has been given to us. And so let us see what happens. So we will be using two molecules of the starting material that has been provided, and these two molecules, if you write it in a proper orientation type of manner, you will see that this reaction would actually become pretty clear. So as you can see that if you write it in this manner, then on the application of NOET, which is practically a base, ETO minus, it would actually form the negative charges as adjacent to the C double bond OET groups, and those negative charges would actually attack, and it would form the NOET group. Okay. So as you can see that the negative charge I have positioned in a wrong manner. So the negative charge would be in the adjacent to CO2Et. Okay, anyways, so then this would actually give us the CO2Et oriented compound, which on hydrolysis will give us the two COH groups, and these are beta keto acids. So these readily decarboxylate into the diketone compound, the dicarbonyl compound, which on Clemmensen reduction, corresponding Clemmensen reduction, would actually give us the cyclohexane. Yeah, so in the second reaction, the Claisen rearrangement happens. So you just give the proper negatively charged compounds and it will get it. Okay, so in the third question, let us see, we have got orthoxylene, which has been given to us, and we have to convert it into the corresponding anthranilic acid. So to perform this conversion, we have to use Hofmann bromamide degradation, and this is a very important reaction because even the second part of this reaction is a question by itself. So we'll be using the Hofmann bromamide degradation. So as we can see that we have got this the orthoxylene compound. We'll first oxidize it using potassium dichromate and H2SO4, and this oxidizes the corresponding methyl or the alkyl groups into the C double bond OH or the carboxylic acid. So we get to the dicarboxylic acid compound, and after heating it we actually get the dehydrated compound, which is the acid anhydride. So we'll be getting this acid anhydride, which when applied or reacted with ammonia NH3 gives us the C double bond NH, and this when actually reacting, not NaOH Br2. So first we will be applying NH3 to this, and this should actually give us the corresponding C double bond NH, and this compound, which is the phthalimide compound, when reacting with the NaOH Br2, would actually first apply the NaOH as base, which will actually open the phthalimide ring, and that would give us the C double bond O minus and the CONH2 corresponding. After that, the NaOH Br2 forms the NaOBr, which undergoes the Hofmann bromamide degradation, that actually converts the amide to the amine, the C double bond NH2 to NH2. Hence we get the C double bond O minus NH2, and after acidic workup in the last step we get our desired product, which is the anthranilic acid. Yeah. So this was a very interesting reaction, and as you can see, this phthalimide compound, this phthalimide to anthranilic acid, is also a separate reaction, as I was saying. So this is a very important and significant question. Practice it well. Okay, so going to the fourth question, we have to convert furan to alpha naphthol. So this is also a pretty interesting reaction, and we will be using a very well-known name reaction, which is the Diels-Alder cyclization, which is 4+2 cycloaddition reaction, and we'll be using that particular reaction here. So firstly we will be reacting furan with benzene, simple benzene. So let us see that what is happening in the reaction. So we have got furan, and we'll be reacting it with the simple benzene, and we'll apply heat, and it will form the 4+2 cycloaddition. That is the Diels-Alder reaction, as I said. So let us see if we write it properly in proper orientation for carrying out the Diels-Alder reaction. We can actually see that this forms another 5-membered fused ring. So we will get that ring, and there will be the O in between, the bridge of the oxo bond in between. On the application of acid, we will actually protonate that particular oxo, and it will form the OH plus, which would undergo the re-aromatization in the following manner, as is shown in the arrow posing mechanism. And this re-aromatization gives us the alpha naphthol, which is our desired compound in this particular reaction. So yeah, so this is also a very important and very interesting reaction. So let's go to the fifth question, which is the last question in this set. So as we can see that we actually have here the mesithyl oxide, and we have to convert it into the diamidone. So these are very well-known carbonyl compounds and unsaturated carbonyl compounds. For this we will use a combination of Michael addition at first. As you can see, 1,4 addition would be needed, conjugate addition would be needed, and then we will be using an intramolecular aldol type of reaction, which would happen in between in the next step. Okay, so let us see. So we have the mesithyl oxide compound, and we will be using diethyl malonate, and this actually will be using with NaOET. So firstly, as we can know, that this is actually basically an activated methylene type of compound, where the methylene H are actually pretty acidic in nature, as they are beside the two ester groups. So firstly, what happens is a negative charge is generated in the diethyl malonate, which actually attacks in a 1,4 conjugated manner, and this is actually known as the Michael addition part, Michael addition reaction. After that, let us see what happens. What is the Michael addition product? We will first check it out. So this is actually an enolate that has formed, and this enolate also rearranges due to the presence of ETOH, which can act as a proton donor, and hence what happens is that it becomes the keto-enol tautomerism happens, and we get the normal keto group. And after that, we know that adjacent to the keto group there are also 3 protons present, and on the application of NaOET, which is the base, another proton is abstracted from the keto part, and what happens is that we end up with the perfect setup for an intramolecular aldol type of condensation with the ester group that is present. And what happens is the OET actually leaves, and we are ending up with a dicarbonyl compound having an ester functionality in. Now, as you can see, when acidic power curve is taking place, then what happens is that the ester compound actually transforms into the corresponding acid, and as you can see, this is the beta keto acid, which once again when heated undergoes a ready decarboxylation due to the formation of a 6-member transition state, and we end up with our desired compound, which is the diamidone. Yeah, so this is the answer. So thank you everyone, and please follow and subscribe for more such videos. And I apologize if there is any mistake in any question. So you can see that those questions are pretty important and interesting. And as I always say, that keep writing organic chemistry reactions. It's imperative that you write organic chemistry reactions. Practice well. Thank you.